Hello guys, welcome to the DMS online school. If you are new to this channel, you are most welcome, and on this channel I teach mathematics, science, biology, and also revise past examination papers just as I'm going to do now. If what I do on this channel is what you're interested in, please consider clicking on the red subscribe button below and also turn the bell notification so that YouTube notifies you whenever I upload a new video. Mind you, I'm going to upload also the prediction for science, prediction for biology 2022 for internals. So for you to be notified when I upload, you must actually subscribe and turn on the bell notification. So the paper reads Science Paper 1, the paper that was written on the 2nd of August 2022 by the GCE candidates. So the paper reads Examinations Council of Zambia, Examination for General Certificate of Education Ordinary Level. So without wasting much of your time, let's go straight into the revision. All right, so this is section A, 20 marks. Answer all the questions on the answer grid provided in this question paper. A1 reads, which of the following is not an example of a basic unit? Let me read again. Which of the following is not an example of a basic unit? Alright, so you must understand what a basic unit is. A basic unit is actually an SI unit that is used to represent a fundamental quantities or basic quantities. What are these basic quantities? These are quantities like mass, time, length, current, temperature. Then we have amount of substance. We have also light intensity. So these ones which I've mentioned, they are considered to be fundamental quantities in science, and their units are known as basic unit. So the question says, which of the following is not an example of a basic unit? So when we look at ampere, ampere is actually an SI unit for current. Current is actually a fundamental quantity. Then meter is actually an SI unit for length, and length is actually a fundamental. Then second is actually an SI unit for time, and time actually is a fundamental quantity. All right, then we have watt is actually an SI unit for power, and power is not a fundamental quantity. So when they say which of the following is not an example of a basic unit, then watt actually is not. So let's answer A2. A2 reads, the following diagram shows a broken rule used to measure the length of an object. Let me read again. The following diagram shows a broken rule used to measure the length of an object. All right, so we have a broken rule here, and this broken rule, as you can see here, it is broken, and here it is being used to measure this object here. Then the question says, what is the zero error and the actual length of the object? What is the zero error and the actual length of the object? All right, we must understand what the zero error is. So the zero error is actually an error that is caused by a measuring instrument when it does not start from zero. Like this broken apparatus here, since it does not start from zero, it contains actually a zero error. So a zero error is an error caused when an apparatus or measuring instrument does not start from zero. So this is what we are saying. Zero error, we are saying it is an error caused when the measuring instrument does not start at the zero mark. Yeah, so in this case, we have to know what the zero error is. All right, so the zero error here is actually 3.8 centimeters. So how do we know where the instrument starts from? Here, that's where the zero error is. So the instrument starts on this line here. So consider that going left of this ruler, there are numbers like 0, 1, 2, 3. So all those have been cut. So for you to reach 4, you need to have 3. Then you have these small graduations. They represent actually 0.1 each. So for instance, here we have 4. So this is 4.1, 4.2, 4.3, 4.4, 4.5, 4.6, 4.7, 4.8, 4.9, then we have 5, then 5.1, 5.2, 5.3, 5.4, 5.5, 5.6, 5.7, 5.8, 5.9, 6. So you see now where our instrument is starting from on this line, it is almost like which line? This one here. So this line is a 4.8. So this line will be 3.8 because 3 is this side. So this is our actually zero error for this broken rule. All right. So then the question is saying what is the zero error and the actual length of the object. So then the actual length or the reading, the actual length or reading here is equal to actual reading or length is equal to, we are supposed to say reading shown, the reading that we can see here minus the zero error. So the reading is equal to, when you look at this line here where the object ends from here to here, so we have if this is a 4, then we have 4.1, 4.2 up to 5.9. So our reading here is actually 5.9. Then we are going to subtract the zero error, which is 3.8. So 5.9 centimeters here minus this value here 3.8, we are going to obtain 2.1 centimeters. So this means that our correct answer here is zero error 3.8. Here they're saying plus, minus, then actual length is 21. So our correct answer is actually this one here, A. So let's go to question number 3. So this is A3, which reads, a person dropped an orange from a basket on his head 1.8 meters to the ground. A person dropped an orange from a basket on his head 1.8 meters to the ground. With what velocity does it strike the ground? All right, so an object is being dropped from the head, an orange actually, then a height of 1.8 from the ground. Then they're asking us to calculate the velocity with which it strikes the ground. So the formula for calculating velocity is actually this one here. Velocity is equal to square root of 2 times the acceleration due to gravity times height. So this is our formula actually, and maybe I can show you where this formula is coming from. Maybe let me get this a book of mine. Where is it? Here it is. So I just want to show you this formula. Where is it? Okay, so the formula is somewhere here. Let me just scroll a little bit up. Falling object, free falling objects. So for free falling objects like the one we are talking about, an orange, they are guided by these equations. So for free falling object, like these are the equations. So we have this equation here and also this equation and this equation. Now for an object here, let's come just here. So yeah, for an object thrown downward, for an object thrown downward or dropped, it's the same as dropped. So initial velocity becomes 0. So this value here becomes 0. So if initial velocity becomes 0, equally here it is 0, then all these formula changes. So here it is 0, so this formula becomes this one, then this formula becomes this one, then this formula becomes this one, which is the one actually that I used in answering that question. Actually, this is my book that I use written by myself. All right, so let's go back to that. So this is the formula. V is equal to square root of 2 times A, I mean G, acceleration due to gravity, and H, height. So when an object is dropping, it accelerates with an acceleration called acceleration due to gravity. And even if here it has not been mentioned, like it is mentioned in other questions where they give you acceleration due to gravity, you must know that you must use it. It was just a slip of an examiner not doing that. So here you are going to say V is equal to square root, then 2, then acceleration due to gravity must be known to be 10 always, then times height, which is 1.8. So you say equals, you multiply 2 times 10 times 1.8, you get 36, square root of 36, you get 6 meters per second as the velocity with which the orange strikes the ground. So our answer is C. Then F4 reads, the following graph shows how the speed of a car varies with time. The following graph shows how the speed of a car varies with the time. All right, so here we have on the vertical axis velocity, on the horizontal axis time. So the question says, what was happening to the motion of the car between 10 seconds and 20 seconds? The acceleration of the car was, so let's go back, between 10 seconds and 20 seconds. What was happening to the acceleration of the car between this portion of the graph? So what you should know, guys, on a velocity time graph is that if you have an upward straight line like this one, it represents actually acceleration and constant acceleration and actually increase in speed. When you have a flat or horizontal line, a horizontal straight line like that, it represents actually a constant velocity or speed and 0 acceleration. Then a downward straight line like this represents actually constant deceleration and also a decrease in velocity or speed. So those are the conditions you must know. So between 10 to 20 seconds, here actually the object has 0 acceleration. So when they say the acceleration of the car was actually, it was 0 here, D. Alright, so guys, as usual, when I'm answering, don't consider that my answers will always be perfect. I'm human. I'm also prone to making errors. So most of the time I do notice that I do make errors, and most of you, those that follow the videos, are able to correct me in the comment section, and I'm able to notice that. So like in the previous video where we revised Science Paper 2 GCE 2022, there was this question here, question number 20. And on this question number 20, I gave an answer as this one, but this is not what I had actually intended to, not knowing how I arrived on this one. The actual answer for this question actually must have been this question here, D. Actually the answer was D, not this answer here, because we have actually an acid and what, and an alcohol, so they will not provide these kinds of bond here. So they may provide these kinds of bonds here, which confused me with this. But however, this an alcohol actually loses an acid loses OH, while this one just loses H. So that's why this end should have, if it loses OH, it remains with OC. So this end OC. Equally, this one, it will be used to join. Then this end, if it loses H, it remains with O. So this one becomes the correct answer for that question number 20. Then there was another question from section B, which was the B1, where I defined the diffusion as the movement of particles from a region of low concentration to a region of high concentration. Again, I made an error. I didn't realize that I was making an error, but now I realize I thought I was saying it's the movement of particles from a region of high to low, but not knowing that I was saying from a region of low concentration to a region of high, which is not true. The correct answer should have been the movement of particles from a region of high concentration to a region of low concentration. All right, now that I've corrected the errors that I made in the previous lesson, let's continue with the revision. All right, so we are on F5. So F5 reads, a uniform plank is pivoted at its midpoint. Two weights are added to the plank, one weight on each side of the pivot in the position shown in the following diagram. So let me read again. A uniform plank is pivoted at its midpoint. Two weights are added to the plank, one weight on each side of the pivot in the positions shown in the following diagram. So we have this uniform plank here with actually two weights on either side of the pivot. So we have this weight here, another weight here. Then the question is saying a vertical force is applied at end X to balance the plank. What is the size and direction of this force? All right, so this is the force they are talking about that is being applied at X here to balance the plank. So the plank remains in its state of balance as it is. So now for us to be able to know this force here, since this question is coming from moments and we are told that for the plank to balance, then we must use the principle of moment, which says for an object to remain in equilibrium, meaning the sum of the forces acting on it must be equal, or rather the clockwise moment and the anticlockwise moment must be equal. So in form of an equation, the principle of moment says anticlockwise force times the distance of the anticlockwise force from the pivot is equal to the clockwise force times the distance of the clockwise force from the pivot. So this A stands for ant, this C stands for clock. So we have these forces here. Clockwise moment is the rotation which can make this plank to rotate in the clockwise direction, or like in the direction the clock rotates. Then anti-clockwise moment or rotation is that rotation which causes it to rotate in the opposite direction in which the clock rotates. Like this force here can cause an anti-clockwise moment like that, and then this force can cause a clockwise moment. So this force here is on this side here. So what we do according to principle of moment, it should be like the sum of the anti-clockwise moment here must be equal to the sum of the clockwise moment on this side. So here we have two forces, this force here causing anti-clockwise, and then this force which we do not know whether it is causing clockwise or anti-clockwise. We are not very sure, but it is only the left side of the pivot. So what we are going to do here is to say X here, which is X, find its moment. So the moment of X is the X at 4 can produce actually a moment, and that moment will be the force itself times its distance from the pivot. Also, this force here produces a moment, and that moment can be the force itself times its distance from the pivot. And also this force here can cause a moment, and that moment can be the multiplication of the force itself times its distance from the moment. So now we are going to apply the principle of moment. So the moment on the left side must be equal to the moment on the right side. So the moment on the left side, there are two. There's a moment being caused by this force 12 and the moment being caused by a force applied at x. So the moment being caused by a force applied at x is going to be x times the distance of x from the pivot here. It is actually 2 plus 2 is the total distance of x from the pivot, which will be 4. Then this is the moment caused by the force at x. Then that moment plus another moment which will be caused by the force at here, which is the 12 force. So we'll say plus this moment here caused by 12, so 12 times also the distance of this force from the pivot, which will be 2. Then we'll say equals this one here. Then we'll say this force also, which is 8 times its distance from the pivot, which is 2. All right. So now, the moment we substitute these values like this one ceases to be physics. Now it becomes a mathematical problem, in this case an algebraic expression. So what we are going to do here is to say x times 4, which will be 4x plus 12 times 2, 24, equals 8 times 2, which is going to be 16. All right, yeah. So now what we are going to do here, we have 4x plus 24 is equal to 16. So for us to know what x is, we must make x the subject of the formula. So we are going to collect like terms together. This number and this number must be on the same side, which is the right side of the equal sign. So we'll remain this side with 4x equals 16. This, when it crosses, it becomes negative 24. Then 4x is equal to 16 minus negative 24, it will be 8. Then we'll divide by 4 to remain with x here, also here by 4. Then 4 into 4, it will cancel, remain with x is equal to 4 into negative 8, negative 2. All right, so once we have that one, what now we are going to do is to know that our force now is actually negative 2 Newton now. The question is, can we have a negative force? Never. It just shows that since this other force here, it is positive, but this force has got a negative value, it means it is acting in the opposite direction as this force here. So they're in opposite. So this force is facing downward. For this to be acting in the opposite direction, it means it is acting upward like that. So this is acting upward, this downward, so they are balancing this one here. So when they say what is the size and direction of this force, we are going to say the size of the force is actually 2. Here we have 2, 2. Now it is going to be upward, which will mean that our answer is going to be B. So let's move to question A6, which reads, the following diagram shows a small pickup weighing 5,000 Newton approaching a hill. It moves up the hill at a constant speed. All right, so we have a pickup. So when they say the following diagram shows a small pickup, it's actually a car weighing 5,000 Newton approaching a hill. It moves up the hill at a constant speed. So this is a pickup of 5,000 Newton as its weight. Then it is going up the hill with constant speed. Then they are asking us to find if the gravitation field strength is 10 Newton per kilogram, calculate the work done in moving the pickup up the hill. If the gravitational field strength is 10 Newton per kilogram, calculate the work done in moving the pickup up the hill. So work, we know it as the work is equal to force times the distance. So which will be equal to, now again they have given us a weight and then they have not also given us the force. So the weight actually, it will also help us to know that actually they are asking us to calculate the work done. So you use this one here, because if this is its weight also acts vertically upward like that, vertically straight. That's how weight of an object acts. So this is the distance actually moved by the force. When we say work is equal to force times the distance moved in the direction of force. So the force, which is weight, its direction is this, because weight is like force of gravity, and force of gravity acts vertically up or down. So the distance is actually this one. So we'll get the 5,000 Newton times the distance, which is 10. Then when we multiply 5,000 times 10, we'll get 50,000. And then when you check, our answers are all written in standard form or scientific notation. So we can convert this one to be 5.0 times 10 to the power 3. So we are just moving a point here. 1, 2, 3, 4. It lands there. So we'll say 10 to the power 3 joules as the units of work. So our answer is what? A. All right, so let's move to question A7. Question A7 reads, the following diagram shows a simple machine. The following diagram shows a simple machine. So we have a simple machine here. So the question says, what type of a simple machine is it? So when we look at this one, it's a wheelbarrow with a wheel and handles. So what type of a machine is this one? Is it a gear, lever, a pulley, or wedge? So actually, this one is not actually a gear. Any simple machine which has a pivot like this one here, and the point where force is applied, it's actually a lever. So a wheelbarrow is actually an example of a lever. So our answer is B. So let's go to A8. A8 reads, the following diagram shows boiling water and ice in a test tube. The following diagram shows boiling water and ice in a test tube. All right, so we have this is a test tube. Inside of it, some boiling water. Down here we have ice cubes. Then we have a wire gauge here that is actually dividing water and the ice, so that ice cannot float because it's light. And then we are seeing some heat here, and then we are seeing some boiling here, and then we are seeing some steam here, but ice is still existing while this side it's boiling. Then they're saying, what is the aim of this experiment? To show that, so this experiment is actually used to show that water is a bad conductor of heat. Yeah, so water is a bad conductor of heat. They're saying heat cannot travel downwards, ice cannot melt in boiling water, steam is a good conductor. No, it's actually D. Water is a bad conductor of heat, because if it was a good conductor, this heat would move this way and also melt the ice. But since the ice is not melting, meaning water is actually a bad conductor of heat. So let's go to question A9. A9 reads, which of the following equations best describes Charles's law of thermodynamics? Which of the following equations best describes Charles's law of thermodynamics? All right, so these thermodynamics equations they're talking about, actually they have advanced the terms here. What we use are actually the laws of gases. That's what I know. But now they're using another advanced term, thermodynamics, just to confuse a GCE candidate, because I don't think in physics grade 11 we use this word as thermodynamics in those textbooks. We have what we call gas laws, and the Charles law is one of the gas laws. Thermodynamics is used at tertiary level, like at college and also university. So anyway, they want us to actually see which equation here best describes Charles law of thermodynamics. So these laws, which are gas laws, are quite complicated to remember, and their equations actually. So me, what I use are these initials B, C, G, and what helps me to remember these are what I have given these initials to represent. So B stands for beautiful, then C cute, then G girls, then I say off, then I have these initials which I say T, P, V, and these letters actually represents T represents for 10, then P pro, then V says. So I read altogether this as beautiful cute girls of 10 provinces. Of course, yeah, I appreciate those beautiful cute girls of 10 provinces of Zambia. So now, what do these now stands for in relation to gas laws? So B stands for Boyle's law, then C Charles law, then G gas law, then T stands for temperature, P pressure, V volume. So what I do, I connect this with that. So if I connect B with T, so it reads Boyle's law at constant temperature. That's what I read. Boyle's law at constant temperature. Or I read it in another way. Let me say it in this way. For a fixed mass of a gas at constant temperature, Boyle's law at constant temperature, or for a fixed mass of a gas at constant temperature, Boyle's law says pressure is inversely proportional to volume. That's how I read it. Pressure is inversely proportional to volume. So this one, it means Boyle's law at constant temperature, for a fixed mass of a gas, then pressure will be inversely proportional to volume. This one, you must just understand that pressure is inversely proportional to volume, meaning when you increase pressure, you reduce volume. When you increase volume, you reduce pressure. That's how it works. Then this one, C connects with P. So again, I say for a fixed mass of a gas at constant pressure, then temperature is directly proportional to volume. So according to Charles' law, then temperature will be directly proportional to volume, meaning if you increase the volume of particles of a gas, then their temperature will reduce. Again, if you decrease the volume of those particles, temperature will increase. Also, when you increase temperature, volume will increase. When you decrease temperature, volume will decrease. So this is what we are dealing with here. But let me explain also. G goes with V, and also this one reads for a fixed mass of a gas at constant volume. According to gas law, temperature is directly proportional to volume. So when you increase temperature, temperature is directly proportional to pressure. When you increase temperature, pressure also increases. When you decrease temperature, pressure also decreases. So now, as we are dealing with this one here, Charles' law, for a fixed mass of a gas at constant pressure, we are saying temperature is directly proportional to volume. So we are going to say, I started with volume. It's a similar. Volume is directly proportional to temperature. Now we can drive an equation. How do we drive an equation? By actually saying V, where there's this proportionality constant, we put equal sign. Then according to variation, when we put equal sign, we put K, then we put T. That's what it means. Then this equation, if we try to make K the subject of the formula as they've made these, so here we divide by T so that we remain with K, here also with T. So here we have V is equal to, okay, here we have only K, then here we have over T, like that. So when we look at this equation, it resembles which one? It resembles V over T, right? B. So this will be now the equation that describes Charles' law of thermodynamics. So let's move to 10. So let's push 10 up a bit. So A10 reads, the following diagrams show thermometers used in a school laboratory. The following diagrams show thermometers used in a school laboratory. So we have these thermometers here, TU, VW. Then the question says, which thermometer has the greatest range and which thermometer has the greatest sensitivity? All right, so for us to be able to answer this question, we must understand what a range is and what sensitivity is all about, or what constitutes a range and what also constitutes a sensitivity where a thermometer is concerned. So I'll start with a range. Range is the difference between the lowest value and the highest value. So for instance here, the lowest value is 0, the highest value is 20. So 20 minus 0 is actually 20. So the range for this thermometer is 20. For this one, 0 to 40. So the highest range is 40. For this one, it is from 0 to 300 to 200. So the range is 200. This one is from 140 to 300. So for us to know the range here, we are just going to say 300 minus 140 equals, so here the range is 60. So this is the range. So now we know here 40, here 20, 40, 200, here 60. So this one has actually the greatest range. Now what constitutes sensitivity in a thermometer? So for a thermometer to be said to be sensitive, it must be able to read or to show reading for any small change in temperature. So any small change in temperature on a thermometer, the thermometer must be able to give you the values. All right, so for it to be able to give you the values, unless the graduations or the marks on the thermometer are very close to each other. So when you check on these thermometers here, the one with markings that are very close to each other is actually thermometer T. Here we have 0, 5, 10, 15, 20. Here we have 0, then we go to 30. Here from 0 we go to 50. Here from 0 we go to 140, we go to 180. So there are big differences in markings here. So these won't be sensitive, but this will be sensitive. So the one with the greatest range is a V. The one with the greatest sensitivity is actually T. So TV, greatest sensitivity is T, greatest range it is actually V. So our answer is B. So let's go to question number A11. Question number A11 reads a wave. So question number A11 reads question A11 reads, a wave of frequency 13,000 Hz travels 1,300 meters in 2 seconds. What is the wavelength of the wave? A wave of frequency 13,000 Hz travels 1,300 meters in 2 seconds. What is the wavelength of the wave? Alright, so for us to be able to calculate the wavelength or find the wavelength, we must use what we call the wave equation that you must know. So the wave equation says velocity is equal to frequency times wavelength. So this is the wave equation. Now, for us to be able to use the equation, unless we know all the data which we are supposed to use in this equation, so we know velocity. Do we have velocity here? No. F frequency, do we have it? Yes, 13,000 Hz. Then this one, lambda, stands for wavelength. So this wavelength is what the question is saying. What is the wavelength? So first of all, we need to know velocity. We have not been given, but have we been provided information to help us find velocity? Yes. So if a wave of frequency 13,000 Hz travels at 1,300 meters in 2 seconds, then we can find the speed here, because the speed is equal to AC is equal to distance over time. So this is what the speed is. So here we are using velocity, here speed. Velocity and speed are the same. In terms of magnitude, they only differ in direction. So velocity is a vector quantity, which means that it also supposed to have direction, while velocity is just a scalar quantity. That means it only deals with the magnitude or size. So here, don't get confused. If I find speed, put it here thinking what is going on. No, they are, in terms of magnitude or size, they are just the same. So speed is equal to distance over time, where we'll say speed is equal to distance we have been provided, 1,300 meters. We'll put there divided by time we have been provided as seconds. So we'll say speed is equal to 1,300 divided by 2, will get 650 meters per second as our speed. Then after that, we should make this lambda or wave length the subject of the formula. So we'll start with this part here containing the wavelength. We'll start with it. We'll say frequency times wavelength is equal to velocity. Then for us to remain with wavelength, we'll divide by frequency here, even here by frequency. So frequency and frequency will cancel, remain with wavelength is equal to, then we'll have a velocity divided by frequency. So now we have made the wavelength the subject of the formula. Now we can substitute. So we'll say wavelength is equal to velocity is the same as speed. So we'll say 650 divided by frequency, which is 13,000. We'll put 13,000. So when we divide 360 by 13,000, we'll get 0.05 meters as the wavelength, which means our answer is A. All right, so let's go to A12. So A12 says light travels from air into a glass block of refractive index 1.5 as shown in the following diagram. So let me read again. Light travels from air into a glass block of refractive index 1.5 as shown in the diagram here, the following diagram. So we have a glass block here, then you have an incident ray traveling from air. They didn't even label, but they're saying from air, then it's actually entering into the glass block. So this line here represents what we call the normal. The normal is always at right angle to the surface. Then this ray is called the incident ray, and the angle between the normal and the incident ray is called the incidence angle, or the angle of incidence. Then the angle between the refracted ray, this ray is called the refracted ray. The angle between the refracted ray and the normal is called angle of refraction. So the question says calculate the angle of refraction in the glass block. Calculate the angle of refraction in the glass block. So for us to be able to answer this question, we must know what relates angle of incidence, angle of refraction, and refractive index. So that equation which relates these is called Snell's law, which says refractive index used by this symbol is equal to sine of the angle of incidence, I stands for angle of incidence, divided by sine of the angle of refraction, R here. So now we know this one as refractive index being provided as 1.5. So say 1.5 is equal to, then we know sine, this angle of incidence is 60. So say sine 60 divided by this angle, we don't know it, which is actually angle of refraction we are trying to find. So we'll write it as it is. Then what we are going to do, we'll need to make this the subject of the formula. So we'll say divided by 1, then you cross multiply 1.5 times sine r, you have 1.5 sine r, then you say equals, then 1 times sine 60, you have sine 60. Then to remain with r, we are going to divide sine r, we will divide by 1.5, even here 1.5, so meaning this and that they will go, so we'll have sine r is equal to, so we'll say sine 60 divided by 1.5. Now we don't need sine, we need r, so to remain with r, I'll say r is equal to, this sine becomes sine inverse, so it will be sine inverse, like sine to power -1 is read as sine inverse, then we say open brackets, these will be in brackets, sine 60 degrees over 1.5. So from here what we are going to say, a refractive angle or angle of refraction is equal to sine inverse, open brackets, we'll say sine 60, which is going to give us 0.866. Of course, I rounded it off, but it shouldn't be like that. You don't need to be rounding off values before you find the answer. So if I say sine 60, I come on trigonometry sine, I found the answer to be 0.866 with these values. So I was trying to save for space here, that's why I decided to round this to 3 decimal places like that. But it's not a good practice in science to be rounding off values before you find the answer. That causes the final answer not to be accurate. So you must avoid rounding off too early, as I did. I did it because of space, but you don't need to do that. So this is the sine 60, you get 0.866, then divided by actually 1.5. All right, so what you are going to do, you say angle of refraction is equal to sine inverse of, so you divide 0.866, so you say, where am I? I'm here. So I'll say this one now, I'll say divided by 1.5 equals, so I got something like 0.57735, so I just ended somewhere there here. Then once you find that one, what you should not do now, you use the inverse now. So you say, this calculator of course and yours are different, so with me on your calculator you should go on the there's a function which we call shift, then me I'll go on this one, shift, which is second shift, I think that's what it means, second shift. Then I'll say sine inverse this one, then my answer becomes 35.26, so of which I gave as r is equal to 35. So when you check on the option, we have 35 degrees, which means this is the angle of refraction. All right, so let's go to A13. So A13 reads, a person standing 150 meters from the front of the cliff claps his hands once and hears an echo after 0.9 seconds. Find the speed of sound in air. Okay, let me read the question once again. A person standing 150 meters from the front of the cliff claps his hands once and hears an echo after 0.5 seconds. Find the speed of sound in air. All right, so we know the formula for speed is equal to, speed s is equal to distance over time. All right, so for us to be able to solve this question accurately, we need to create this situation here. So we have a cliff is actually a mountain with one straight side, which is this one as a cliff. Then this side is actually the cliff of the mountain. The straight side of a mountain is actually called a cliff. This side is a flat, this side is a straight, so this side is called a cliff. So there's a person standing here, and the distance, a person standing 150 meters from the front of the cliff. So this is the front, so he's standing at 150 meters. Then he claps his hands once and hears an echo after 0.9 seconds. So if he claps, so his sound will go like that. This is his sound. Then he will hear an echo, meaning sound will go and come back. That sound which reflects here is called an echo. So he hears it after 0.9 seconds. So after he claps, the sound goes like that. So from the time sound goes and comes back to his ears, 0.9 seconds elapses. So when they say find the speed of sound in air, speed is equal to distance over time. But what you should notice is that the distance here that has been covered by this sound actually is from here. Sound went like that, it bounced, it came back to this person. So what distance has it covered? When it was going, it covered 150. When coming back again, another 150. So you are multiplying distance times 2 here. So you say this formula changes as the speed is equal to 2 times d over time. Then now you take it here, you say speed is equal to 2 times distance, which is 150 here, over time, which is 0.9 seconds. So you say equals, so what you are going to do when you evaluate everything, you'll find that you have a 333.333 like that, which you can round off according to one decimal point. So it will be 333.3 meters per second, which will mean that the correct answer is D here. Alright, so A14 reads, which of the following does loudness of sound depend on? Which of the following does loudness of sound depends on? Is it amplitude, frequency, pitch, or wavelength? Actually, the loudness of sound depends on the amplitude. Alright, so guys, if you are finding value in this video, please give it a like and let me know in the comment section. And if you haven't yet subscribed up to this time, please consider clicking on that red subscribe button below. It is for free. If you have downloaded the video, please go back to this video, click on the subscribe button, turn on the notification, also like the video. And also what you should do is, when you do that, it is to comment in the comment section, so that you don't miss when I upload another video. YouTube is going to send you a notification when you switch on data that the DMS Online School has actually uploaded another video, and you'll be able to see that video. And if it is a prediction, then it is going to guide you how you should prepare for the exams. Alright, so let's go to question A15. Alright, so A15 here reads, the following diagrams show a small compass close to a strong bar magnet. The following diagrams show a small compass close to a strong bar magnet. So we have these bar magnets here, this one, this one, this one, this one. Then they're saying which diagram shows the correct compass direction. Which diagram shows the correct compass direction? Alright, for us to be able to tell which is the correct compass direction here, unless we remember in class when we were looking at magnetic fields around a magnet, if you remember quite well, you must have done with your teacher how magnetic fields flow. You must have been told that magnetic fields around a magnet flow from the north to south. They flow from north to south like that. And if they flow from north to south, how do we know? We use what is known as a plotting compass. So when you put a plotting compass, especially at the north what we notice here is that it actually faces the other way, like this one here. That's how it used to face until it was able to point in the direction of field from north. That's how the pointer does. It points into the direction of field from north, going like that. So it used to go like that. So the answer actually is this one, which diagram shows the correct compass direction is actually D here, guys. That's what you should know. So let's go to A16. A16 says a negatively charged rod is held close to but not touching an insulated metal sphere as shown in the following diagram. A negatively charged rod is held close to but not touching an insulated metal sphere as shown in the following diagram. So we have here, this is a rod which is negatively charged. So charged rod here with those lines, those are minus line, it means it is charged negative. And this is a metal sphere. This one, they have labeled it metal sphere here. So they've held this negatively charged rod close to the metal sphere but not touching an insulated metal sphere. So this one, they're saying it is insulated, though they did not indicate here. We usually indicate its insulation. Now the question is saying which diagram shows the correct charge distribution on the sphere. Which diagram shows the correct charge distribution on the sphere? All right, so when you look at these two, the charged rod, negatively charged rod, and the sphere, this is charged, this is not charged. It is neutral because we can't see the charges there. So in any object that is neutral, that means it has equal number of positive and negative charges. So that's why it stays negative or neutral, I mean. Now whenever you bring a charged object close to something which is neutral, then there's induction of charges in that object which is neutral, following the law of electrostatic or static electricity. So like this, the law of static electricity states that like charges repel while unlike charges attract. So if you were to bring this one closer, here you know that they are positive and negative. So those negative that are here, they'll be repelled because they are like with this. All right, so they are alike with these here, so they will be repelled to the opposite end of the sphere. So when they get repelled here, the positive ones will remain here. So this side will obtain an overall positive charge, and this side will have an overall negative charge. So which means that the correct charge distribution that this one is going to have is actually going to be here. All right, so let's go to question 17, A17, which says which of the following circuit diagrams shows all the three resistors in parallel? Which of the following circuit diagrams shows all the three resistors in parallel? So we have this one. Parallel is when current does not pass in all. Not one current should pass in all. So current should reach a junction, some current goes in another resistor, another one in another one. Or in other words, parallel connection is where resistors are not following one after the other, but they're standing side by side. So when you look at these resistors here, they're following one after the other, they're not standing side by side. Here they're following, like this one can be said to be following this and also this, but these two here are not following each other. So only these two are parallel, they're standing side by side, but if current passes like this, it can enter here and some can enter. So this one is in series with this and this, but these two are in parallel. But they are asking us to identify the ones in which all the three resistors are in parallel. So here again you find that this one is almost like this one. So this diagram and this one, they're one and the same thing. So this one actually they're standing side by side. So current when it reaches the junction, it divides, some goes here, some here, some here. So this one is the correct diagram for resistors, all three of them in parallel. So our answer is D. Then in A18, let me push it up. So A18 reads, an ideal transformer has an input voltage of 12 volt and an output voltage of 240 volts. It has 2000 turns in the primary coil. Find the number of turns in the secondary coil. So let me read again. An ideal transformer has an input voltage of 12 volts and an output voltage of 240 volts. It has 2000 turns in the primary coil. Find the number of turns in the secondary coil. So what we are going to use here is what we call the transformer equation. So the transformer equation states that voltage in the primary coil divided by voltage in the secondary coil is equal to number of turns in the primary coil divided by number of turns in the secondary coil. Alright, so now we are being asked to find the number of turns in the secondary coil here. Number of turns in the secondary coil. So we must make number of turns in the secondary coil the subject of the formula. So what we are going to do is to first substitute. So an ideal transformer has an input voltage. So input voltage is always the primary voltage or voltage in the primary coil. So if they say an ideal transformer has an input voltage of 12 volts, so this input voltage should be in the primary coil. So where there's V primary, we are going to put 12, then over, and an output voltage of 240 volts. So output is for the secondary, so we have 240 is equal to it has 2000 turns in the primary coil. So in the primary coil we have 2000 turns over, find the number of turns in the secondary coil, we don't know, so write NS. So we'll make this the subject of the formula by multiplying this times that. We'll get 12 NS is equal to 240 times 2000 there. Alright, so next we should divide by 12, also by 12, so that we remain with NS. So here 12, here 12, so here NS is equal to, so here what you should do now, you do it once. So what you can do here, let me clear this. So you say open brackets, so you say 240, that is not 240, 240 times, then you say 2000, right? Alright, so then you close bracket, so you are dealing with this one up first, then you say divided by, if you want you can also put it in a bracket, 12 here, okay, then you say equals, so you get your 40,000. So it means here number of turns in the secondary coil will be 40,000 turns. So our answer is going to be C there. So let's go to 19. So 19 says, A19 says, which of the following radioactive emissions has the strongest ionizing effect? Which of the following radioactive emissions has the strongest ionizing effect? So ionizing or ionization is the process of making a substance charged. Alright, so which one of these, X-ray, gamma ray, beta and alpha, has the strongest effect or strongest ionizing effect? In fact, the one with the strongest ionizing effect among these four here is actually alpha particles. So alpha particles are positively charged and they're heavy, so when they move they knock off electrons from particles they come across, because they are positive, so they attract those electrons, making those other atoms charged or ionizing them. Alright, so let's now answer 20. A20 reads, radium has a half-life of 1600 years. Calculate the number of half-lives it will undergo for a 100 gram mass to reduce to 12.5 grams. So let me read again. Radium has a half-life of 1600 years. Then calculate the number of half-lives it will undergo for a 100 gram mass to reduce to 12.5 grams. All right, so you must understand the concept of half-life, guys. So the concept of half-life is just so simple. I did a video already about it, so you can check around my channel. I think you'll be able to find that video actually talking about half-life and other things. So half-life is actually the time taken for a radioactive sample, or for the original amount of a radioactive sample to decay by half. So if you are given 100, the half of 100 is 50. So if this sample has to undergo radiation so that it decays from 100 to 50, the period that has taken to decay from 100 grams to 50 grams, we call that time period as half-life. And we are told the radium here has a half-life of 1600 years. It means if you have 1000 grams for it to go, 100 grams for it to go to 50, actually these are the number of years that must pass for it to have so many years, so it does not decay so frequently. But the question is quite a different one. So they are saying calculate the number of half-lives it will undergo for 100 grams, for 100 grams mass of 400 mass gram to reduce to 12.5 grams. All right, so what you should do is just get 100. So this 100 grams must reduce to 12.5 grams. So it must move from 100 to 12.5. So you must know that the first half-life, if it has to take place, this one must reduce to 500. For it, another half-life, if you divide this one, it goes to 25. If you divide this one, that's when it goes to 12.5. So now when they say calculate the number of half-lives, how many half-lives has it undergone? So you have 1, 2, 3. So you have the first half-life here, the second half-life, the third half-life. So there are 1, 2, 3. So there are 3 half-lives, which means your answer is A. Alright, so we are done with the section A, guys. So give it a like if you are enjoying it, if you haven't done so. And also, if you haven't subscribed, please consider clicking on the red subscribe button below and turn on the bell notification. Remember, subscription is for free. You don't pay anything. But if you cannot subscribe, that means you don't have a Google account or a Gmail account. Alright, so let's go straight now into section B. Alright, so here we are in section B, 45 marks. Answer all questions in this section. Write your answers in the spaces provided in this question paper. So let's start with B1, which reads, figure B1.1 shows a simple pendulum suspended on a clamp stand for determining the periodic time. Figure B1.1 shows a simple pendulum suspended on a clamp stand for determining the periodic time. So they haven't suspended it on a clamp stand here. There's no clamp stand. They forgot a lot of things. Nevertheless, the question is just okay as it is. So we have this one is a support to which a simple pendulum is suspended. So it is oscillating between position A, B, C. Then A, they are saying what is meant by periodic time of a simple pendulum. So what is the periodic time of a simple pendulum? So we are saying this is the time taken to make a complete oscillation. So it is actually the time taken to make a complete oscillation. So what is a complete oscillation? It's a full swing. When this one swings from here to C and back to A, that is what we call an oscillation. And the time it can take for this to oscillate to C and back to A is what we call periodic time, or time period as we know it. All right. So B, state two factors that do not affect the period of a pendulum. So which two factors do not affect the period of the pendulum? One, we are talking of the mass of the bulb. The mass of this bulb does not affect the period of the pendulum, and then also the amplitude also of this does not also affect the period of the pendulum. All right, so let's move to another part, which is actually C. C says this experiment is done on Earth and repeated on the moon. One, where would the periodic time be higher? Okay, so if it is done on the moon and then on Earth, where will the periodic time be higher? So periodic time will be higher on the moon. So they are saying justify your answer in one. So this is because the acceleration due to gravity is less on the moon, and this results in a longer period. Yeah, so maybe to just make you understand what is at stake here, what you should understand here is this, that periodic time, which is T, is equal to 2 pi, then square root, then we have length over acceleration due to gravity. So if you are doing an experiment, what we do when we are doing an experiment, we just measure length here. So if you have length, I think, yeah, and then acceleration due to gravity. So on the moon, the acceleration due to gravity is actually small as compared on Earth. So G on the moon is actually 1.6, somewhere there, Newton per kilogram. But on Earth, it is 10 Newton per kilogram. So you notice that it is bigger. So if you have a smaller value, here is point. If you have a smaller value, you are using the same length here. While if you use same length here, and then I don't know here, maybe I'm leaving R here, maybe there's something I might be leaving out in this equation, but the point is here. So if you have same length on Earth and on the moon, but here on the moon, here you have 1.6, on the Earth you have, so any value here divided by a bigger value like this one, the result in this under square, it will be bigger when you use this one than when you use this one, and that value you find here is going to affect everything here. So that's why the answer is saying this is because the acceleration due to gravity is less on the moon, and this results in a longer period. All right, so let's move to the other question. Okay, so we go to question B2, which reads, figure B2.1 shows an apparatus Elena used to measure the mass of an irregular object. So let me read again. Figure B2.1 shows an apparatus Elena used to measure the mass of an irregular object. So take G to be 10 Newton per kilogram. Okay, so this is an irregular solid being placed on this apparatus here, which is the balance, and the mass there is 350 grams. Then A says what is the weight of the irregular solid. So weight is given by mass times C, acceleration due to gravity. So weight is going to be equal to mass, which is 350. So 350 is in grams. Mass is always measured in kg as its SI unit. So this 350, convert it in kg. How do you do it? By dividing with 1000. So if you say equals, so this is the mass you are going to use, which will be actually 0.35. So here the mass 0.35, then times acceleration due to gravity is 10. So which will imply that weight is going to be 0.35 times 10, it will be 3.5 Newton as your weight. So let's move to B. So B here, they're saying the learner measured the weight of an object on top of Mount Everest and also down the same mountain using a spring balance. The learner measured the weight of an object on top of Mount Everest and also down the same mountain using a spring balance. So one, they're saying what was his observation about the two weights. So what this person observed is that the weight of an object on top of the mountain was lesser than the weight down the mountain. To give a reason for the learner's observation, we are saying this is because acceleration due to gravity decreases with the height or altitude. Yeah, so the higher you go, the lower the acceleration due to gravity is. And remember we said weight according to the formula again is equal to mass times what? Height. So because when you go on the top of the mountain, acceleration due to gravity will be lesser, so that value multiplied by this will give you less weight. So that's the very reason for this. So let's move to another question, which is B3. B3 reads, figure B3.1 shows the graph of a car that moved from a residential area into town. Figure B3.1 shows the graph of a car that moved from a residential area into town. All right, so this is the figure: velocity on the vertical axis, time on the horizontal axis. Then we have A, B, C, D. Then they're saying A, describe the motion of the car from 1 AB. So AB. So just as I said, if you have a velocity time graph like that, an upward straight line like this represents actually increase in speed of velocity. So since here we have velocity, so this is an increase in velocity or constant. This is increase in velocity or constant acceleration. So AB actually stands for the car has constant acceleration. Then BC, I said this one represents constant velocity here. So where there's constant velocity, there is actually no acceleration. So BC represents constant velocity, so the car has constant velocity. Then CD, actually we say this is actually constant deceleration, so the car has constant deceleration here. So let's go to the other part, being what was the acceleration when the car was moving with the constant velocity. So when the car is moving with constant velocity here, what is the acceleration? Here the acceleration is always 0. So here we are going to say the acceleration of the car was 0. So let's move to B4. So B4 says figure B4.1 shows a seesaw balance with forces as indicated. So figure B4.1 shows a seesaw balance with forces as indicated. So we have a seesaw here. All right, so we have this force here, anti-clockwise force, being balanced with these two forces here, 150 and 110. Then the distance of this 2000 force from the pivot is 2 meters. The distance of the 150 force from the pivot is y. The distance of 110 force from the pivot is 2 meters. Then the question says the 200 Newton force is 2 meters from the pivot. The 150 force is y meters from the pivot, and the 110 force is 2 meters from the pivot. Then A, state the principle of moment. So we said the sum of the clockwise moment is equal to the sum of the anticlockwise moment. Yeah, this is the principle of moment. The sum of the clockwise moment is equal to the sum of the anticlockwise moment. Then let's push this one here where they're saying calculate distance y. So we'll bring the diagram back. So they're saying we calculate this distance y here. So for us to be able to calculate distance, we are also going to apply again, just as we did in section A, we are going to apply the principle of moment, which says a force clockwise force times the distance of the clockwise force from the pivot is equal to the anticlockwise force times the distance of the anticlockwise force from the pivot. So however, when you check on this side, we have two forces. So the sum of the anticlockwise force must be equal to the sum of the clockwise moment. So the sum of the anticlockwise moment must be equal to the sum of the clockwise moment. So here there are two forces that are causing the moment that can cause this one to go like this. There's this force and this force, so you add them. So we are saying this side is clockwise, so this side is what causes clockwise like this. So we are starting with this side. So we have this force, which is 150 times the distance of 150 from the pivot is y. Then we'll say plus this other force here, plus 110 times the distance of 110 from the pivot is 2. Then we'll say equals, then we'll have this side now, we'll have 200 times the distance of 200 from the pivot is 2. Then from there, what we are going to do is to do now simplification. This is now an algebraic problem. So say 150 times y, 150y, then plus 110 times the 2, which is 220, equals then 200 times the 2, which will be 400. Then here we'll make 150y the subject of the formula, so numbers should be on the right side of the equal sign. So say 150 is equal to 400 minus 220 here, which will be 150 equals 180. So divide by 150 here, 150, so that we remain with y only. So y is going to be 1.2 meters. So that will be the distance there, guys. 1.2 meters y. Calculate the distance y, 1.2 meters. All right, so find the force x acting upward. Okay, so let's push this one up. So they're asking us to find this force here acting upward. Find the force x acting upwards at the pivot here. So for us to be able to answer this one, we need to use Newton's third law of motion, which says to every action force there's an equal but opposite reaction force. To every action force there's an equal but opposite reaction force. So these forces that are pushing it down here, there must be another force that is acting in their opposite but equal to this but opposite to their direction, and that is x. So using that law, we are going to say total upward force, which is for x, is equal to total downward force, these which are acting downward. So we'll say upward force is just x is equal to downward force is this force plus this plus this. So we'll have 200 plus 150 plus 110. So when we add these, we are going to get 400. So this force now is going to be negative 460 Newton, meaning that it is actually pointing in the opposite direction. These are positive, so this is negative, pointing upwards. All right, so let's move to another question, which is question B5, and it reads: an 8 kg brick fell from a building under construction. The brick fell from a height of 80 meters. Take G to be 10 kilogram, Newton per kilogram. Then they're saying A, calculate the potential energy. So calculate the potential energy just before it started falling. All right, so potential energy just before it started falling. So what you should know is that potential energy is the energy an object has due to its position on the surface of the earth. So if something is lying exactly on the surface of the earth, like on the ground, then it has no potential energy. If you put the book on the ground, it has no potential energy. If you put it on the table, then it has potential energy. So that potential energy is actually because of the height it has. So equally, they are saying an 80 kilogram brick fell from a building under construction. The brick fell from a height of 80 meters. Take G to be 10 Newton per kilogram. So they say A, calculate the potential energy one just before it started falling. So before it started falling, the height it was at 80 meters high. So the formula for potential energy is equal to PE, standing for potential energy, is equal to mass times acceleration due to gravity times height. So say equals mass is 8 times acceleration due to gravity is 10 times height is 80. So when we multiply this, we are going to get potential energy as 6,400 joules. Then 2, after falling halfway down. So after falling halfway, meaning the height is actually 40. Now instead of 80, now it's at 40. So the potential energy is just going to be half of this. So say potential energy is going to be 6,400 joules divided by 2, which is going to be equal to 3,200 joules. Then B, calculate the kinetic energy of the brick after falling for 3 seconds. So we need to calculate the kinetic energy of the brick after falling for 3 seconds. So what is kinetic energy? Kinetic energy is just an energy an object in motion possesses. So any object that is in motion or moving object possesses a certain type of energy, which means kinetic energy, because the word kinetic just means motion. So energy related to motion is called kinetic energy. So that is stone, when it is falling and it is moving, so it will have now kinetic energy. So they're saying calculate the kinetic energy of the brick after falling for 3 seconds. So as it was falling, time passing here now was 3 seconds. So during that falling for 3 seconds, what is its kinetic energy? So we must know that kinetic energy is equal to half mass times velocity squared. So here we need to know first velocity. So since this stone is falling, remember that formula I said velocity is going to be equal to gt. Since we have been provided with the time, so velocity is going to be gt. Where is in my book? Did I close it? No. So this time around we are using this formula here. So this formula has become, this one has become this one here. All right, so it has become this one, this formula, because if it is falling, then this initial velocity here becomes 0. So if you put 0 there, naturally then this formula reduces to v is equal to gt. So we are using this formula around because we have been given time. The other time we used this formula here because we were not given time, but we were given height. So these formulas change depending on the whatever information you are given. All right, so this is my book actually written by myself. So now this is the formula. So we're going to say v is equal to acceleration due to gravity is 10 times t, which is time, 3, which will give us V is equal to 30 meters per second. So we know velocity, so say kinetic energy is going to be equal to half times mass, which is 8, then times velocity, which is 30, then you say squared, then you say kinetic energy is going to be equal to 3,600 joules. All right, 3,600 joules. Now, does it make sense? Yes, it makes sense. So let's go to another question. Question B6A says, what is boiling? What is boiling? So guys, boiling is the change of state from liquid to gas without a change in temperature. So this definition actually here doesn't really make sense to someone who is not sure, but what you should know is that whenever there is change of state, temperature stays constant. That's what it means by without change in temperature. So I can also say boiling point is the change of state from liquid to gas at constant temperature. For example, if you are boiling water, boiling point of water is at 100. When you reach 100, temperature stops changing until all the water has evaporated into gas. So that's what we mean by this statement. So boiling is the change of state from liquid to gas without a change in temperature. Or if you are not comfortable with this definition, you can use this one. Boiling is the change of state from liquid to gas at the boiling point or constant temperature. Then B, state two factors that affect the boiling point of a liquid. So one factor is temperature, another factor is pressure. So you can also mention another factor, which is actually impurity. So impurities also affect, or purity also affect the boiling point of a liquid. If it is pure, it will have a different boiling point. If it is impure, it will have a different boiling point. All right, so let's go to C, which says explain the two differences between boiling and evaporation. So the differences are that boiling occurs at a fixed temperature, while evaporation occurs at any temperature. Then 2, boiling occurs throughout the liquid, while evaporation occurs at the surface of the liquid. So you find that boiling will occur at a fixed temperature, like 100 degrees Celsius for water, but evaporation occurs at any temperature. Like in the morning, you check in the river, there's just evaporation going on. So those are the differences. Then boiling occurs throughout the liquid. When a liquid is boiling, you see bubbles inside the whole liquid. That's what boiling is. So boiling occurs throughout the liquid, while evaporation occurs at the surface of the liquid. So you see at the surface just some particles escaping after acquiring some more kinetic energy. All right, so let's go to B7. So B7 reads, figure B7.1 shows the brightness of the electromagnetic radiation with different wavelengths. All right, so this question is actually new. It has never been asked before. These are the questions that we have seen. They are not new. They have been asked in so many different ways, but this one is actually entirely new. So in each and every exam, there are entirely new questions that are done, maybe one or two. Yeah, so now it's very important at this point to tell you guys that you might fail this question, but if you fail like to answer this question, which may have only 5 marks or 6, that cannot make you to fail the entire exam just because this question is new in the exam. So what point am I making? The point that I'm making here is that whenever you are going through an exam, there will be always questions that you are already familiar with them, although they are being asked in a just different way. So if you are one of those that is trying to revise so that you prepare yourself for the coming exams, I'm advising you to get a revision package that I have, which is actually going at the 60 kwacha, which consists of science paper 1 and 2 examination questions that have been answered. Like I've answered this one from 2015 to 2021. So that package, it contains explanation step by step as how to answers have been found, and if you go through it, the probability that you are going to pass with a distinction is very high, and the probability that the least grade that you are going to get in that is just a merit. If you revise with that revision package for science, then the probability that you can get a distinction is high. So only 60 kwacha, prepare yourself for the exam for once and for all, so that you achieve that goal that you want to achieve to get a distinction in science. I also have a revision package for biology, so if you are also preparing for biology, also you can ask for that revision package for biology, just going at 30 kwacha. All right, so these are promotion prices. They were at 160, now they have been reduced to actually 60. There was a period where I took them to 30. I've taken them to 60 because they are very, very variable. They have value in them. All right, so I've made the point here. So let's try to answer this question that came new. So let's analyze. So the vertical axis represents brightness, then the horizontal axis represents wavelength. So question A says, from the graph determining the wavelength where the radiation is brightest. All right, so this is radiation, this brightness, this is wavelength. So this curve represents, when it goes up, it means brightness is increasing. When it goes down, brightness is decreasing. So at which point is the highest brightness? As at this point here. So when we come down where we are supposed to know wavelength, we should come down here at this line here. So when we check, there's this line, there are these lines where they've put numbers actually. So like this line here is actually 1.0 times 10 to the power negative 6 meters. Then after this, there's this line here, which is 2.0 times 10 to the power negative 6 meters. Then after this line, there's this line here, which is also 3.0 times 10 to the power negative 6 meters. Then after this line, there's this line which is at 4.0 times 10 to the power negative 6 meters. So if this point is the brightest point, if we are to come down at this point here, what wavelength does it represent? So what we are going to say, if this is 1, then this is 1.1, this is 1.2. So it will be 1.2 times 10 to the power negative 6 meters. So the wavelength when the radiation is brightest is actually 1.2 times 10 to the power negative 6 meters. Then B says, if the wavelength of visible light rays are between 4.0 times 10 to the power negative 7 meters and 7.0 times 10 to the power negative 7 meters, what is the name of the radiation in A1 above? So they want us to know the name of this radiation here. All right, so now for us to be able to know these, first let's line up this value in a better way we understand. So we know that 1.2 times 10 to the power negative 6, written in another form, it will be 0.000012 meters. Then if we pick this value here, 4 times 10 to the power negative 7 meters, if we are to rewrite it like this, it will be 0.000004 meters. If we are to get this value, it is going to be actually 0.00007 meters, right? So now the point that I'm going to use to know which radiation is this, is the point that when we have radiation, we have about the 7 radiation that we have about 7 of them. So the radiation which has longer wavelength is actually the radiation with a longer wavelength are those actually that are at some other extreme ends, and those with a shorter wavelength are at the other extreme ends. So like if I am to get this wavelength here for this, compare it to this, you find that this one has how many zeros after the point? 1, 2, 3, 4, 5, 1. So this one has 1, 2, 3, 4, 5, 6. So if you compare this wavelength and this one is longer than this. All right. So now this one is a range from this to that. So from this to that. So we have this one 0.000 again, like that. Again, this one is again smaller or shorter than this. This is longer, but I can still relate this one if I am to round this figure here so that it aligns with this number here. I can have 0.0010 meters. Still more, this one is still less than this, but now it means that this and this are almost neighbors. All right, so meaning this visible light should be a neighbor to this radiation here. So which radiation is neighbor? Which radiation neighbors visible light, and that radiation has at least a longer wavelength than that of visible light. So which radiation is that? For you to know that radiation, you must actually use this simple way of remembering this electromagnetic radiation, where we say roast maize is very unusual X-mass gift, where roast stands for radio waves, maize stands for microwave, then EZ stands for infrared, then very stands for visible light, then unusual stands for ultraviolet, then X-mass stands for X-rays, then gift stands for gamma rays. So these are radiation. So these are the ones here. So now the one which is neighboring to visible light here, visible light, we have two. We have infrared and also we have ultraviolet. Now which one is which? So for us to know which is which, we must first know that the wavelength of this radiation this side, this radiation this side have longer wavelength, long wavelength and low frequency. So this side you have low wavelength, long wavelength and low frequency. Then down here, as you move from here, you have short wavelength and high frequency. That's how it works. So on this side, so if you are here going this side, you'll be having longer wavelength. Coming this side, you'll be having shorter wavelength. So longer, shorter. So if you go here, you must make sure that this one must have a longer wavelength than this one. If you come this side, this one will have a shorter wavelength than this one. So when you compare this wavelength range for visible light, it is from here to here, and this one now it is closer to this, but this one which is 0.0012 is greater a bit than 0.0010. So meaning this one is a much greater than this one, which is for light. So meaning if light is here, the one with a greater is infrared. So here the answer should have been infrared. All right, so it was a quite tricky question. You need to analyze it for you to be able to answer it. So that's why intelligence of an individual pupil is very important. There are questions that are asked in an exam that the teacher has not taught in a way that you think they should have taught, but when answering such questions, you need to apply your own intelligence. That's why science is quite tricky. All right, so for you to actually have that analysis ability to answer, you must revise as many questions as possible. So let's now move to C1, which says calculate the frequency of the radiation in air. So we need to calculate the frequency. Take speed of light as 3 times 10 to the power 10 meters per second. So now we are calculating frequency. So we know that the wave equation should be speed is equal to frequency times wavelength. So we can make frequency the subject of the formulas. Frequency times wavelength is equal to speed. So we divide by wavelength. So remain with frequency is equal to speed over wavelength. Then what we'll do, frequency is equal to, there the wavelength was 1 point, speed is 3 times 10 to the power 8, this one here. Then the wavelength was 1.2 times 10 to the power negative 6. When you divide these, you get what? You get 250 what is this, billion. Then here I had to put meters, but it should be hertz. We are finding frequency. When we write it in standard form, it is going to be actually 2.5 times 10 to the power 14 hertz as the frequency of this radiation in air. Then 2, they are saying we state one use of the radiation. So infrared, what is its use? So in furnace for car paint, or in remote control for TV, hi-fi, etc. All right, so now let's go to B8. B8 says figure B8.1 shows bar magnets with different poles. So figure B8.1 shows bar magnets with different poles. So we have a bar magnet here, another one here, another one here with different poles. So they're saying identify the following poles: P, this P here, R, this one here, T, this one here, Y, this one here. Okay, so the arrows which they have provided here help us to identify the poles. So we know that field flows from north to south. So like here we have P and Q. So field is flowing from P to Q. So this should be the north. This one is the south. Then here we are seeing field is entering here. So where field is entering, that's where the south is. So R is north, and here also it's south, and here also it is entering. So V is south. Here field is coming out, so T is north, and here it is coming out, so Y is also north. So we are saying A, P, this one here. Where is P? This one P. So since field is entering into P, then P is actually south pole. Then R field also is entering, so it means that R also must be south. Then T, where T field is coming out, so it must be north. Then Y also field is coming out, and it is also north pole. All right, so simple for marks. Then let's move to question B9, which reads figure B9.1 shows a circuit consisting of a 12-volt battery with a combination of resistors between points X, Y, and Z. So figure B8.1 shows a circuit consisting of a 12-volt battery with a combination of resistors between points X, Y, and Z. All right, so this is a battery with a combination of resistor between X, Y, and Z. So we have a combination of these resistors here. So we have 2 ohm, 6 ohm, 12 ohm. And again, this question, we revised it in our revision before the GCE candidates wrote. And those who wrote actually physics, they came and appreciated to say physics was so simple because most of the things that came, we covered them. And that is the power which is in revision, and I'm also asking you to get the revision package so that you get advantage of it as you go in the exam. You stand a better chance. All right, so like this question says, calculate the effective resistance between Y and Z in the circuit. So they want to calculate the effective. The word effective resistor actually means total resistance between Y and Z. So total resistance between Y and Z are these resistors here, and these resistors are in parallel. So how do we find the total resistance for resistors in parallel? Is using this formula. R total resistor is equal to, let's say this is resistor 1, this is resistor 2, so we'll say resistor 1 times actually resistor 2 over resistor 1 plus resistor 2. That is actually a formula as well for finding total resistor. So we'll say you substitute, you say total resistor is equal to resistor 1, which is 6, times resistor 2, which is 12, over then resistor 1, which is still 6, plus resistor 2, which is 12. So here you say total resistor is equal to 6 times 12, 72, over 6 plus 12, which will be 18 I mean. Then you say total resistor is equal to 72 divided by 18, which is going to give you 4 ohms. So your total resistance here, or effective resistor, it would be 4 ohms. Then B, they're saying find the current flowing, find the current through the 2 ohm resistor. So what will be the current in this 2 ohm resistor? So for you to know the current in this 2 ohm resistor, first you must know the total resistance in the circuit. Then that total resistor in the circuit will tell you the total current in the circuit, because the current that is coming here, passing here, is the total current that is in the circuit. So a series will tell you like how much total current is flowing. So the total current is determined using the total voltage by also total resistor. So we add this resistor here and these in parallel. So this resistor here and these in parallel, they make a series. So this resistor and these which are in parallel, they're in series. So say total resistor is going to be equal to resistor, let's call this one as 1, and these which are in parallel as 2, which is this one we already found. So we'll say total resistor is equal to this resistor, which is 2, plus then this one we found the total, which is 4, which is going to give us total resistor as what? 6 ohms. Then for us to know now the current, we'll use Ohm's law equation, which says voltage is equal to current times resistor. Then we'll make current the subject of the formula. So current is going to be voltage over resistor. So we'll say current is equal to voltage 12 divided by resistor, which is 6. So meaning current is 2 amps. So I never even indicated here. So current is going to be equal to 2 amps there. All right, so let's move to another question. C, calculate the voltage across this 2 ohm resistor. So this 2 ohm resistor here, what will be its voltage after knowing the current? So simple, voltage is equal to current times resistor. So voltage will be equal to the current flowing here and the resistor itself. So current, we have found it is 2 and the resistor is 2, so times 2, so it is going to be 4. So if here there's 4, then here there's actually 6, 8 actually here. All right, so let's go now to section C. So we are now at section C, 20 marks. Answer any 2 questions from this section in the separate answer booklet provided. So you always answer 2 questions from section C and you answer them on the separate answer booklet. So C1 says a learner carried out a Hooke's law experiment using standard 50-gram masses and obtained the following results as shown in table C1.1. So this is the table having the values on Hooke's law. So here we have mass 0, 50, 100, 150, 200, 250, 300, 350. Load 0, here it's blank. Length of loaded spring in centimeter, here we have 10.00.0. Here we have these values. Here extension 0, then here nothing. Then A says complete the table C1.1 for the values of the load Newton and extension in centimeter. So this one, actually we revised these questions in other questions, and then when they came, those GCE candidates, they really enjoyed this year's exam because it was like they were revising. So that's the power which is there in revision, because when you revise like from 2015 to 2021, definitely there will be questions that will be as though you are revising. All right, so that's why you need a revision package. So for you to contact me for the revision package going at 60, so you must just maybe look at the number in the description. I'm going to leave the number in the description of this video, or in the comment section. I'll put the first comment that I'm going to pin, which will have the number asking for those wanting to get a revision package to WhatsApp me on that number, or maybe I'm going to leave it on the screen throughout. All right, so now when they say complete the table C1.1 for the values of the load in Newton and the extension in centimeter, so let's start with this one. So let's see, begin. So we want to know the load here. So extension, it works like this. When you put something on the spring starts to stretch, and it shows the weight of that object. So here when they're saying mass on the spring here, so mass here actually was what? 0. So that mass brings what we call force. So now here what we are just going to do is to convert these masses into force here. So simple. So what we are going to do, load is actually weight. So this load is the force, and it is a Newton, and it's actually weight. So it is these masses that we are going to convert into weight. So what we do, we use the formula weight is equal to mass times gravity. So these will convert them like they're in grams. So like 50 here, 50 is just going to be 50, you convert it into kg first, so you divide by 100. All right, 1000 I mean, so that you get 0.05, so which will be the mass now in kilogram. So if you put it here 0.05, then you multiply g, which is acceleration due to gravity, which is always 10, so you get your weight as what? 0.5. So here now the load is going to be 0.5. So equally this one you do the same. Let me also show this one so that the rest you work out yourself. So this one, I'll say 100 divided by 1000 equals that one 0.1, then it times again 10, so it will give you what? 1. So here you have 1. If you work out the same way we have done here you have 1.5, here 2, here 2.5, here 3, here 3.5. Then here extension, now here we need to work out extension. So extension, when a spring, something is put on it, it starts extending. Now when here it was 0 load, there was no load, the spring was already reading as 10.0 centimeters in length already. So now this 10 meaning it was the origin. Okay, twalaisa tumweve first impwishayo. Okay, so yeah, so this since C is a reading that showed on the spring when it was not yet loaded, there was no mass, then this one can be considered to be the starting point. So we can consider this 10 as the starting point, so 0.0. Now when they loaded this, the spring stretched from 10 to what? 12.2. So from 10 to 12.2, what is the difference? So you say 12 minus that 10, you get 2. So equally, when they loaded this, it went to that. So that minus that, you get that. So you start separating that minus that, you get that, until you get all the values like that. So that is it. So this required you to get 2 marks for doing that. So let's see the other part. B, use the values obtained in A to plot the graph. Use the values obtained in A to plot a graph of extension C in centimeters against load newtons. So we'll push this here. So bring these values in this table. So we plot extension against load. So bring a graph here. Then on this graph, it is extension against load as the title. Don't write title extension against load. Don't do that. Just write extension against load. It is known that this is the title. You never go in the book where they say title, then they even write the title there. No, they just write the title. Everyone, as the virtue of it being at the beginning of the topic, you call that as the title, beginning. So this is extension against load as the title, which is a feature of a graph. Then this vertical axis, they're saying extension. Then here we must have load. So here label it extension in centimeters. Here you must have load in newtons. So that's how it is going to be. So now what you should now do next here is to make sure that the values that you are going to allocate here, so this one is always 0. So the values that you should allocate on the load, for instance, they must be able to accommodate 0.51, 1.52, 2.53, 3.5. So the largest value you have is 3.5, which will make your work easier. So if you say this is 1, 2, 3, 4, 5. Bola yali pomporoka. So if the values you have are 0.51, 1.52, 2.53, 3.5, the largest value you have is 3.5. So you make sure that you fit this data here. So if I said this one is 1, 2, 3, 4, can this data fit here? Yes, because the largest value I have is 3.5. But here my largest value is 4. So these are my points here, like 3.5, 2.5, 1.5, 0.5. These are my 0.5. They'll fall into these small lines here. That's why they are there 4. You see how they work. So because I'm emphasizing, because a lot of you have problems in terms of plotting information on a graph. So this is why I'm going to emphasize. Then also on the extension, you are using these values here. So the largest number you have is actually 11. Yet here you have 1, 2, 3, 4, 5. So for you to accommodate this 11, you are going to break this one into another way. So you say this one should be 2, 4, 6, 8, 10. Then this one should have been 12. So you have surpassed actually 11. So 11 meaning will be within these values here, or will be able to be found within this range. So after you do that, now you start plotting this comma this extension or load comma this. So if you come on load, you have 0.5. So this is the side of the load. So if this is 0, this is 1, then this represents, so this one will be 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1. Then 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, 2. I'm reading these to show you how they are actually matching. They are making sense. You don't do things like anyhow. Then, so you are plotting 0.5 against 2. So 0, so you say 0.1, this line, 0.2, 0.3, 0.4, 0.5. Against it 2. So when you go straight, 2 is here on the extension side. So you plot here. This is 0.5, 2. 0.5, 2. Then you come to 1, 4. So 1 on the load is here. Then 4 is actually here. So this one is straightforward here. Then 1.5, 6. So 1, 1.1, 1.2, 1.3, 1.4, 1.5, 6 here. Then here 2.8. 2.8 simple like that. Then again you say 2.5, 9.5. So 2.5 is here. Then remember this is 8. So if this is 8, now what do these smaller values represent, these small boxes here? Since we said this is 2, so for you to understand how these small box, each box here represents 2 units. So you say here 2, 4, 6, 8. Let me just come closer, it's quite tricky. So let me first use this one, maybe here. So this is 2, 4, 6. Okay, so I will say 0, 0.2, 0.4, 0.6, 0.8, 1, 1.2. Okay, let me just remove this. Let me temporarily remove my highlighter so that I make sure that it's not going. I need to turn on my highlighter, turn off. Okay, then I come here, then I pick this one. Yeah, so I start counting nicely. So this is 0, 0.2, 4, 0.4, 0.6, 0.2, 0.4, 0.6, 0.8. Then this is 1, 1.1, 1.2. This is 1, 1.2, 1.6. 1, 1.2, 1.4, 1.6, 1.8, 2. That's how it is moving. Yeah, so why I'm doing that, it's because I want you to understand one thing here, because we are going to plot 2.5, 9.5. So 2.5 is here. So if we have this 2.5 here, this is 8. So we'll say 8.2, 8.4, 8.6, 8.7, 8, 9, then 9.2, 9.4, 9.5 is on the middle here. So that's why we'll put 9.5 there. This 9.5. So you have to be very careful. Then also now, let me use which one is a little bit bigger. Okay, also now we come to 3,10.5. So 3 is here. Then 10.5 again, let me pick that smallest one. So 3.5, 3 is here. Then this is a 10, 10, then this one is 10.2, 10.4. Then 10.5 is somewhere on the middle here where there's no line. So that is where 10.5 is. Then 3.5, 11. So 3.5 is on the middle here. So if this is a 10, you say 10.2, 10.4, 10.6, 10.8, then 11, 11.2, 11.4, 11.5 on the middle somewhere there. Or just 11, not 11.5. So this is 10, 10.2, 10.4, 10.6, 10.8, 11 on that line there, 11. So it was small for me because I'm doing it on the screen. So I wanted to accommodate, if it is on the graph, I should have used bigger values than what I've used. So let me now bring back my highlighter. Okay, so now we will draw now a line like that. Okay, you've seen you draw a line joining these points. So the line must join these points like that. They are not even going smooth. What is going on? Like that. Good. So next, let's go to another question, which is C. On your graph, show the elastic limit. So we have plotted this one. So on our graph, we'll show now the elastic limit. On your graph, show the elastic limit. So an elastic limit is a point at which the line stops being straight. So from here up to here, the line is still straight. From here, it is not straight. So here, that's where the elastic limit is at this point. Elastic limit, we will point it like that. So let's go to another question. Saying from the same graph, show the load when extension is or was 9.0 centimeters. So when we come, if extension is 9.0, so extension 9.0 is here, then what should have been the load is when you move 9.0, then you reach the line, you drop down here, you find that the load would have been 2.1.2.3. So it will be 2.3 there. So you said load is equal to 2.3 newtons. Then you go back. The other question says, state the condition under which Hooke's law is obeyed. So for Hooke's law to be obeyed, you must know that it is only obeyed when the spring is not stretched beyond its elastic limit. So state the conditions under which Hooke's law is obeyed when the spring is not stretched beyond the elastic limit. That's when Hooke's law is obeyed. The moment elastic limit has been reached, Hooke's law does not apply, meaning extension is not directly proportional to the force. Like here in our situation here, like even if we have found this answer, like, it's not really a correct answer as far as experimental measurement are concerned, because in experimental measurement, for them to be correct, there must be actually before the extension limit. Then let's see, we are done with this one. Let's go to another question, C2, which says, during an experiment, a learner used a liquid in a glass thermometer to check on how heat was affecting the temperature of water. Then they're saying table C2.1 shows temperature of water at specific times. So, okay, during an experiment, a learner used a liquid in a glass thermometer to check on how heat was affecting the temperature of water. Table C2.1 shows temperatures of water at specific times. So these are temperature of water, time and temperature of water. At 0, temperature was 21.5, at 60, 27. So as temperature was increasing, as time was going increasing, temperature was also increasing. Then A, they are saying, what is temperature? So temperature is a measure of the degree of hotness or coldness of an object. Or this second one is the mature definition. This one is for the younger one. This one is for the elderly one. So you can use this one, or equally this one. So temperature is a measure of the degree of hotness or coldness of an object. Or temperature is a measure of the average kinetic energy of the particles of a substance. This is actually college level. Then let's go to another question. B1 says, plot a graph of temperature in degrees against time in seconds. So let's plot these values on the temperature against time on the graph. So temperature against time, then here vertical axis horizontal, so vertical temperature horizontal time, so here always 0. So again, see how I'm going also to fit these values. So like here, temperature is here, the lowest value I have is 20, then the highest I have is 53. So I am moving, if I wanted, I could have started from 20 here, going like that, but I didn't actually even use that advantage. So I just said I'm starting from 0 up to 50, somewhere there. So if you have 0, then I need to go to 50. So what I did, I said, okay, this will be 10, 20, 30, 40, 50, but I'm ending at 53, but I still have these lines which can still give me 3. 53 is in between these lines here. Then here I am moving from 0 to 360. So meaning how many hundreds are there? So I can just give this value into bulk. So since I don't have other small numbers after the zeros here, so I can just say this one is 100, 200, 300, and forget. This one can be 400, but still more, 360 can still lie in between these lines here. So I hope you are noticing this. So then from here, what you should now understand, what I've done here is, if I'm at 0, this is 100. I've said then the box represents 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. That's how I reach at 100. Alright? So again, in the similar way, I go to 200. In the similar way, 300. Similar way, 400. Then here, if I have 0, here I have what? 10. So what are these boxes? So each box represents 2. So I said 2, 4, 6, 8. Oh, not that. It represents actually 0.2. So 0.2, 0.4, 0.5. Oh, not that. It just represents 1. each box represents 1, so it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, up 20. That's how it is going. So I've matched my data such that when I begin plotting, no hassle I'm going to encounter. So here I'm plotting time here 0,21. So 0 is here for time, 21 will be here. So this is 20, this line will be 21, so I'll put a dot here for 21, although the graph moved a little bit. Then here I'll say 60,27. So if this is 60,27, I'll say 10, this line, 20, 30, 40, 50, 60, 60,27, I'll say if this is 20, then I'll say 20, 21, 22, 23, 24, 25, 26, 27, there. You have seen the way it is flowing very nicely. Then here 120,32. So this is 110, 100. So this one will be 110, 120. This line here, though it is faint, but just get the concept. So 120,32. So 120,32, I'll go with it. This is 30, 31, 32, somewhere there. So that's how I plotted all the lines like that. This other line, they were found like that. Then after that, you draw the best fit line joining all the points, a straight line. So it will show that here you need a straight line like that. Now when you are drawing a line, if you see that some of the values are not falling under the line, then you draw what we call a best fit. Like this one is a best fit line in which some points here, like above this side, have 1 point remaining, and down here have a point remaining. So meaning this my line is the best fit line. All right, so now we are done. This one will give you 4 marks. Is it how many marks? 2 marks. Plot a graph of temperature against that, 4 marks. Then use the graph to determine the temperature of water at 210 seconds. So when you are at 210 seconds here, 210 is somewhere here, this line 2, then this 210 seconds. So when you are at 210, you come here, then when you meet this line like that, this 210, then you go this way. The temperature here is actually 40, so you say 40 degrees Celsius. Then we come to another question here, C2, which says C1, which says it was observed that at 75 degrees Celsius the temperature of water stopped rising while the supply of heat continued. Explain this observation. So if the temperature is not rising while the heat is still being supplied, that means there's change of state. All right, so it was observed that at 75 degrees Celsius the temperature of water stopped rising while the supply of heat continued. Explain this observation. So why is this observation? So we said that change of state was taking place from liquid to gas here. So whenever there's change of state, temperature actually stays constant, and this change of state is from liquid to gas. So let's get back to, if the liquid used for the above experiment was pure water, state why it boiled at 75 degrees Celsius. So like why it could have boiled at 75 degrees Celsius when we know that water boils at 100 degrees Celsius. So we could say that pressure is one of it. So atmospheric pressure was lower than usual. All right, so the atmospheric pressure was not high, it was low, so water was able to evaporate when it was being heated before it could reach 100 degrees Celsius, even when it was still pure. All right, so let's go to another question. C3. Suggest a liquid that would have been used in the liquid in glass thermometer for the experiment. So there are two liquids there. We can either use alcohol or mercury. Then let's go to another question, which is the C3, which says figure C3.1 below shows a decay curve for iodine 131 with that formula there. Inside there is 131, 53, 1. So this is actually a decay curve. On the vertical axis we have mass in kg, on the horizontal axis we have time in days. Then we have a decay curve, meaning that the iodine is undergoing radioactivity or radioactive decay. It is disintegrating. Then A1, they're saying what was the original mass of the sample. So the original mass is here. When the time is 0, the mass here is the original mass, which is actually 200 kg. So you are going to say 200 kg is the original mass. So let's answer another one. Part 2, what is the half-life of the sample? So half-life, as we stated earlier, is the time taken for half of a radioactive substance to decay, half of the amount of a radioactive substance to decay. So if original amount is 200, as it is, we have 200 here, then for it to reach to 200, the time that must occur is called half-life. So from here to here, this is where you determine the half-life. So you draw a line from here, you reach the graph. When you reach the graph, you go down. So as you see, this graph won't give us approximate answers. I mean, won't give us very accurate answers, because we do not have other graduations. Like here we have 4, then 8. So in between 4 we should have 4, 5, 6, 7. We don't know where 7 is, so we are just going to be approximating. So here between 4, 8 and 12 we have 8, 9, 10, 11, 12. So this one I approximated where it is landing this time to be somewhere 10. So I said 10 days here. So we might have 8, 9, 10, almost on the middle, 11, 12. So here it is 10 days. Then let's see another question. What quantity of the sample had remained after 24 days? So after 24 days, you come at this days here time, then you draw a line up to reach a graph, then you go there. So what sample could have remained? Again, we are going to estimate here in between. It is not really on the middle, this one. If it was the middle, it was going to be 12.5, but this line is a bit up. So I said this one is going to be somewhere 14 kilogram. So equally, the examiner here, I think they should be having a range of values that you must be giving here. They can say between 12, 14, then 13, 12. If someone gives those values, then they get the answer correct. So these are not exact answers, they're just approximation. Then the other question says, if the sample decayed by emitting gamma rays and an alpha particle to produce a new element X, write an equation for the decay. So an equation for the decay happens like this. So this radon or iodine, when it emits gamma rays, there's nothing that changes to it. It still remains iodine, but its energy levels of its electrons just decreases. But if it emits alpha, then its mass number must decrease. This mass number 131 must decrease by 4. Then this atomic number must decrease by 2, because it emits an alpha particle, which it emits, it's a helium nucleus, which consists of 2 protons and 2 neutrons. So that's what it is. So now I'm going to write this equation here, write an equation. So I'll say, if this is iodine 131.53, if it undergoes decay, by alpha, then this one must decrease by 3. So 131 minus 3, you remain with, by 4, you remain with 127. 52 decreases by 2, you remain with 51. Then plus, this will be the alpha particle, which has 4, 2 here. So make sure what the masses here must balance. If you say 127 plus 4, it should give you 131. 51 plus 2, it must give you 53. All right, so let's go to the last part of this question. C says give 2 examples or give 2 properties of each of 1 gamma rays, 2 alpha particles. So examples of properties, give 2 properties for each of gamma rays. Their property is that for gamma rays, they have no charge, they have strong penetration power. Yeah, so these have no charge and they have strong penetrating power. They are not also affected by magnetic fields or electric fields. Then in these alpha particles, they are positively charged, they have strong ionizing power. They are also affected by the magnetic field and electric field. Then in D, mention 1 use of gamma rays. So gamma rays in the treatment of cancer, sterilization of objects. All right, so sterilization is actually purification of objects, killing germs or bacteria from equipment, especially in hospitals. All right, so guys, we have come to the end of this revision. I hope you have learned something that you are going to use in the exam. And if you did learn something, let me know in the comment section. And please, if you haven't given this video a like, please give it a like. It will help this video to go a long way in the YouTube algorithm. YouTube is going to notice by the number of likes to say this video has got a value, and it is going to show it to even other people. So you can also share it to other people in WhatsApp groups, on other social media, so that even your friends can also benefit the way you have benefited. If you have downloaded it already, please go to the channel you downloaded it from, go give it a like. If you haven't subscribed, please consider subscribing so that you don't miss on the next upload. And again, if you want the revision package, the line is on the screen. You can just WhatsApp me. The package is at not 120, it's actually at 60 kwacha science paper 1 and 2 both, then 30 kwacha, which is actually biology. All right, so guys, bye and see you in the other predictions that I'm going to give, which are going to come next week, I'm sure.